Welcome to the Deep Dive. We're here to give you that shortcut to being well-informed, getting straight into the source material on key topics. Today, we are literally plumbing the depths. So we're looking at a really important review paper, The Impacts of Deep-Sea Fisheries on Benthic Communities. Malcolm R. Clark is the lead author from 2016.
Yeah, and what jumps out immediately from this paper, it's that deep-sea ecosystems operate on a completely different clock than we do. Our mission today, really, is to unpack this central paradox the paper lays out. Management, works on human timescales, years, maybe decades, but the impacts down there, they can be basically permanent because the ecosystem functions on, well, geological time.
Geological time.
Right. We need to understand why real recovery, is just not a realistic expectation for these deep-sea habitats right now.
That time paradox is definitely the hook. We hear a lot about deep-sea fishing being a problem. And the core issue seems to be targeting these fish, like orange roughy, that just don't reproduce quickly. So let's start there. What exactly are these deep-sea fisheries? And why are they seen as such a massive threat, even if they're a tiny fraction of global catches?
Okay, so the deep sea, generally we mean waters deeper than about 200 meters, so past the edge of the continental shelf. These fisheries, they operate globally, but they tend to focus on very specific areas, mostly the upper and mid-continental slopes and these offshore features like seamounts.
Right, and those are the spots where you find those valuable species.
Yeah.
You mentioned orange roughy, Oreos, Alfonsino. I guess these became big targets after shallower fisheries got depleted.
Exactly, and that's where the vulnerability really kicks in. If you look at the biology of these deep-sea fish, they have what we call low productivity. They grow much slower, they take longer to mature, they live way longer than similar fish in shallower waters. It just makes them incredibly sensitive to fishing pressure.
It's worth stressing the scale again, though. Less than 1% of total global marine catches come from the deep sea. It sounds tiny.
It does sound tiny, but that number can be really misleading. The threat isn't spread out. It's highly localized and concentrated. Clark and his colleagues cite other work confirming this. Destructive gear, especially these big bottom trawls, demersal trawls, they're consistently ranked as the highest threat. And the fishing itself clusters on specific spots, those seamounts, for example. So even if the overall footprint is small, the damage is intense, right where the most fragile life is.
Ah, okay. That puts the small percentage into perspective. It's not about the total volume caught. It's about hitting the most sensitive spots hard.
Precisely. Concentrated impact.
So if the threat is concentrated, let's talk about how it happens. What's the gear doing the damage?
Well, the main culprit identified is heavy bottom trawl gear. Now, the type of damage, scraping, plowing the seabed, it's similar to what happens in shallow water trawling. But the sheer scale and weight of the gear used in the deep sea is, well, it's on another level. We're talking trawl doors that can weigh up to 2,000 kilograms each.
Tons. Just for the doors.
Yeah. And the nets themselves, they're built tough for rough terrain like seamounts. They have these huge rubber or steel discs, rock hoppers, up to 60 centimeters across. The whole ground gear assembly can weigh several tons.
Wow. So you've got tons of metal literally being dragged across potentially fragile seabed structures, maybe a kilometer down. The physical force must be immense.
It is. The direct impacts are pretty obvious.
Yeah.
Scraping, digging into sediments, basically flattening and mixing everything up, homogenizing it. But here's a key difference in the deep sea. It's typically a very low-energy environment, not much current. So those physical scars, they stick around for a very, very long time.
How long are we talking?
The paper mentions studies off New Zealand seamounts, where trawl marks and soft sediment were still clearly visible 5 years after the fishing stopped.
5 years. Just the track marks. In shallow water, that might be gone in a storm season,
Well,
right?
easily. And beyond the direct track, there's this indirect impact, sediment resuspension. Trawling kicks up these massive clouds of mud and silt, plumes maybe 2 to 4 meters high off the bottom. In these low current deep sea areas, those plumes just hang there. They spread out incredibly slowly, potentially smothering delicate filter feeders and other bottom life far away from where the net actually passed.
Okay, now what about long lining? That's often presented as, a lower impact alternative. How does the paper compare it?
Well, the studies do show longline gear has a much narrower footprint. Overall, definitely less impact than a trawl, physically. But, and it's important but, the paper is careful here, less impact is relative. Long lines still cause damage. When they snag on the bottom or when they're hauled up, they can break off or cut through corals and sponges, the very structure-forming animals we're concerned about.
But if those corals and sponges take centuries, maybe millennia, to grow back, is significantly less impact really meaningful in that context?
That's a really critical question, isn't it? And it's one the paper really forces you to think about. If the habitat itself is ancient, then any level of destruction to that structure is ecologically significant, even if it's localized. It really underscores why spatial management, closing areas off completely becomes so important. We'll probably get back to that.
Definitely. Let's shift to the results then, the actual observed destruction of the habitat. Where does the paper show the most dramatic effects?
Unsurprisingly, it's the communities on hard seabeds, those seamounts, ridges, places with complex structures. Bottom trawling there, the paper states, routinely removes most of the benthic fauna. You're essentially wiping out the habitat engineers, the corals, the sponges. They create the three-dimensional homes for everything else. That structure is just gone.
And there's some really stark numbers in the paper to quantify this loss. Like trawled seamounts off Tasmania. They found an average of only 9 species compared to 20 species in similar unfished areas nearby.
Yeah, and the loss of physical cover is just stunning. They looked at New Zealand seamounts. Unfished ones had maybe 12 to 25% cover of stony corals. After heavy trawling, that dropped to basically zero, 0.04 to 0.03%. It's effectively gone.
And the speed. That's terrifying, too.
It really is. The research cited suggests it can take as few as 10 passes with a deep-sea trawl to wipe out coral cover almost completely, going from, say, 15–20% cover down to nothing you can see.
10 trawls. To destroy something that took centuries to build, that really highlights the mismatch in timescales, doesn't it?
Absolutely. And it's not just the corals and sponges. The whole community structure gets altered. The paper talks about this clear shift in heavily trawled areas. You lose the big, slow-growing stuff, the filter feeders, sea star, sea cucumbers, things like that. And instead, you get smaller, faster-growing opportunists moving in. Things like worms, small clams, and interestingly, lots of scavengers.
Scavengers. How does that work? Is it just them cleaning up the mess?
It's partly an indirect effect. When fish are caught and processed on board, the offal often gets dumped overboard. This provides this sort of unnatural, temporary food bonanza on the seafloor. So that attracts mobile scavengers and predators to the fished areas in large numbers, which further changes the food web and the community away from its natural state.
Right, so you're not just removing things, you're actively changing the dynamics, too.
Exactly.
Yeah.
Which brings us back to that core biological problem, the potential for recovery. Or the lack of it. Vulnerability in ecological terms is about two things: how easily something is harmed that's intolerance, and how well it can bounce back recoverability. Deep-sea megafauna, these big structure-forming animals, they score badly on both.
Okay, let's break that down. First, intolerance. What makes them so easily harmed?
Physically, well, think about their shapes. Many are sedentary, they stand upright, and they're often quite fragile, like delicate sea fans, branching corals, big vase-like sponges. They're just physically not built to withstand tons of metal dragging over them. They get crushed or snapped off. On the other hand, the species that tend to tolerate trawling better are usually tough, low-lying, or mobile, like crabs or lobsters that can scuttle away or maybe withstand the impact better.
Okay, so they're physically fragile. But the real kicker, the thing that makes this a potential management nightmare, is the recovery part, their extreme lifespan.
This is where the deep sea just fundamentally differs from almost anywhere else. It's mind-blowing, frankly. These deep sea invertebrates, many of them live for incredibly long times and grow unbelievably slowly. The paper gives specific, measured examples that are just staggering. Black corals, the Leopathes species from Hawaii, they've been dated up to 4,300 years old.
4,000? Wait, 4,300 years? That's older than the pyramids. Are those dates solid? That's hard to even comprehend.
They are solid. The methods, things like radiocarbon dating or using other radioisotopes, they're reliable for these super slow-growing organisms. And it's not just one species. They mention sponges on the Norfolk Ridge living 600 to 740 years. Even relatively common stony corals, Selenocemelia, can live 75 to 120 years. So when you destroy a habitat built by creatures that live for centuries or millennia, well, the capacity to bounce back just isn't there on any timescale relevant to humans.
So given that extreme longevity, what does the paper actually say about the prospects for recovery? What's the forecast?
It's pretty grim. Based on these biological traits, slow growth, late maturity, long lifespans, the prediction is that recovery will take decades to centuries after fishing stops. And that might be optimistic for some species. Crucially, the empirical data we have backs this up. Studies looked at seamounts 5 or even 10 years after fishing had ceased, and they found no consistent, clear signal of recovery among the large benthic animals.
10 years is nothing compared to a 4,000-year lifespan, is it?
Exactly. It's like blinking, functionally instantaneous.
So if the damage is quick, basically permanent on human scales, and recovery is geological. What does this review conclude about management? What can actually be done?
The paper doesn't mince words. It concludes that expecting impacted areas to recover or be restored is, and I quote, unrealistic and acceptable timeframes. Trying to restore them, say, by transplanting corals, would be incredibly difficult and astronomically expensive, likely impossible at scale.
Okay, so fixing the damage after the fact is basically off the table,
Which means the only truly effective strategy is prevention, stopping the damage before it occurs. The extreme vulnerability of these deep-sea ecosystems points directly to spatial management as the primary tool. That means setting up strong and consistent conservation closures, protecting areas, especially vulnerable ones like seamounts and ridges, before they get fished.
but the deep sea is vast and largely unexplored. How do managers figure out where to put these closures effectively? We don't have perfect maps of everything down there.
That's a major challenge. Since we can't survey every square kilometer, the paper emphasizes using predictive tools, things like habitat suitability models. These models use what we know about geology, oceanography, and known occurrences of species to predict where these vulnerable marine ecosystems, or VMEs, the coral gardens, sponge fields, are likely to be found.
So using models to make educated guesses about where the fragile spots are.
Essentially, yes. And then using systematic conservation planning tools, software like Markson has mentioned, to help design networks of protected areas scientifically, to make sure the closures are placed strategically to protect the most important and representative biodiversity hotspots.
Okay, so wrapping this up, our deep dive into the Clark et al. Review really hammers home this fundamental mismatch. Deep sea life operates on geological time, fishing impacts are immediate, and recovery. Not really feasible in human terms.
Right, and the implication is stark. We have to think very differently about activities where the impact is so swift and profound, but the recovery takes centuries, even millennia. This knowledge makes the argument for protecting remaining pristine deep-sea areas incredibly strong. It's really the only workable solution presented.
And it shifts the focus, doesn't it? If we know recovery takes hundreds or thousands of years, maybe future research isn't so much about how fast things recover, but about getting much, much better at predicting where these vulnerable ecosystems are so we can protect them before the damage is done. It leaves you with a heavy thought. Considering a creature like that 4,000-year-old black coral, what responsibility does that put on us right now, knowing our actions today determine what exists thousands of years in the future? Definitely something to mull over.
Thank you for joining us on this exploration of the deep sea, arguably Earth's last and most fragile frontier.
We'll see you next time on The Deep Dives.